Hello everybody, welcome to Mohammed Seymour's Chem 2 course, which is dual credit with Parkland College, and Parkland College calls it Chem 106, Chemistry for Health Professions. As you can see by this slide, many of the careers that are related to the health profession area are going to be the target areas for this course. Many of our examples, many of our applications that we come up with, the choice of topics are all based on trying to prepare people for the health professions. That does not mean that you necessarily are going into the health professions if you're in this course. You can also be here for the chance to get some chemistry college credit by doing the dual credit portion of the course. Without further ado, I'm going to get right into Module 1. Just want to talk to you first about chemistry not being scary stuff that's just in books that nobody uses. Chemistry is used every day in many different fields, especially in the medical field, where nurses and hygienists and various medical personnel are making choices every day about the care of their patients based on their knowledge of chemistry. And so obviously a better knowledge of chemistry makes us better at doing our jobs. Also, it's not just for chemists. A lot of fields use chemistry besides just the chemists themselves. And so a good basic knowledge of chemistry is important for our future careers. Our first module is going to focus on chemistry and measurement. I'd like to first ask you to go back to your memory of Chem 1 and think about some chemicals. Maybe stop the presentation and write some names of some chemicals down. Just ask yourself, how many chemicals can I remember the names of from having learned about chemicals in Chem 1? Now, if you wrote some chemical names down, maybe some of the names you might have come up with were something as simple as water, or table salt, sodium chloride, or maybe you thought about something a little more obscure like hydrochloric acid or sulfuric acid. Various chemicals are involved in our daily lives and in our study of chemistry. Many of the chemicals that are important in the field of health professions are going to be larger organic molecules, particularly like the drugs that we give patients for pain or for treatment, or the various chemicals that are used in the health profession field. If you've had the introduction to the course yet, then you know that 10% of your grade is going to be based on studying a particular chemical, a drug, a prescription drug, and you will be studying that drug in detail and creating a poster about it as part of your 10% of your grade for this course. So a chemical is any material used in or produced by a chemical process. So if a chemical process produces water, that means water is a chemical. Chemistry is in our daily life in all aspects. Farmers use chemistry, fertilizers, herbicides. The use of chemistry in agriculture is quite extensive. Chemistry is obviously in the medical field. Many of the clothes that we wear are artificial chemicals, artificial polymers, like rayon and nylon and acrylic that are made by chemists in factories. Chemistry has a very important impact on our electronic age. Technology, the internet and so forth would not be possible without the chemistry knowledge to create the silicon chips, that the semiconductor materials that are used to transmit knowledge now through the internet. Chemistry is everywhere, and you probably, if you're already working at a part-time job, you're probably using chemistry a little bit in that job already. Now we know that matter is made up of these little tiny particles called atoms that you learned about in Chem 1. that the atoms have various kinds of bonds, ionic, covalent, metallic bonds, and that these bonds cause the atoms to stick together to make larger structures known as molecules. So chemistry is the science where we seek to understand what the matter does, but we come at it from the perspective of what are the atoms and molecules doing. So you have to have a bit of imagination to do chemistry, because you have to imagine these tiny things that we can't even see under a light microscope, like you can see cells in biology, but you can't see atoms and molecules. So you have to have a bit of imagination and use your knowledge of atoms and molecules abstractly to think about what is happening at the macroscopic level, at the large level, with these atoms and molecules interacting. Now, chemistry is a science, so what is science? Why do we need to use science to study chemistry? Science is simply knowledge that we gain by testing and by using the scientific method. It's just a way of obtaining knowledge in a systematic way through testing. For example, let's say we wanted to apply science to ask ourselves, is water A cleaner or is water B cleaner? Now you could look at these two colors and maybe you pick letter B because it's more blue, maybe you pick letter A for some reason, but how would you test to see if water A and water B is cleaner? So there may be a variety of chemical tests you might use. You may examine it through various techniques. And you may test the pH of it. You may test the whether or not it causes any precipitates when you add certain chemicals to it. Maybe you look at it under a microscope. Maybe you look at various properties of the water, look and see if any techniques can be used to separate the water into various parts, or is it mostly just water. But a variety of techniques might be used to determine which water is cleaner. Now if we take these close-up views and look at a little more distance, let's take a look, see what A is. Oh, A is Windex. And B is some nice water at a resort somewhere. So I think we have to conclude that A is, in fact, because it's Windex, A is cleaner. It's Windex window cleaner, right? That would make it cleaner? Okay, bad joke. We need to use the scientific method to eliminate bias or preconceived ideas. If you simply went at knowledge, gaining knowledge randomly, people have these biases, these preconceived ideas. We think we understand the world, but we have to be able to get around that. We have to think about things in a more, we have to pull back from our biases and use a more systematic way. So we're trying to be logical here and not simply use our preconceived notions to guide us here. If we tested our guess on which water was cleaner, we would realize they're not just water. One of them was salt water at a ocean resort somewhere, and the other one was in fact Windex. What are the steps to the scientific method? Well, science starts by observing the world around us. It is important to use our eyes and various measuring equipment to make observations. Without good data, without observations, and the systematic way of recording those observations, we can't really organize what we see in the world around us and try to start to make some sense out of it. Hypothesis is basically an educated guess. We think we understand science, we've observed things, and we're attempting to explain those observations, so we make these hypotheses. Now these need to be testable, so we need to be able to go into the laboratory, test it, and then test it over and over again to see if it always gives the same results. A hypothesis is not a true hypothesis unless it's possible to be falsified. It needs to be falsifiable. In other words, there must be a chance that your hypothesis is wrong. Otherwise, there's no need to test it, and or there would be no way to test it. For example, if I said that everything in the world happens because of invisible little men that nobody can see or detect, that's not a hypothesis that could be proved wrong, but obviously is a silly hypothesis because there's no way to prove it right either. These little invisible people are undetectable. So you can't really have hypotheses that you can't test. Experiments are the way we test these. These are highly controlled. We control as many factors as possible, and then we vary certain factors to see what the effects are. These are meant to test the predictions made by the hypothesis. Now, if our experiments disprove our hypothesis or make our hypothesis questionable, then we need to go back and readjust our hypothesis and replace it if we need to, because experiments don't support it. Now, after a series of experiments, and if our experiments are starting to support our hypothesis, then we might be able to formulate a theory. A theory is the highest form of scientific knowledge. It requires the greatest understanding of what is happening. A theory is basically meant to be an explanation of the observations. Not only are we saying the observations happen, we're saying why they happen. The reason why the chemicals work the way they do are due to atoms and bonds and molecules. These are theories that we have to try to explain the behavior of chemicals, for example. Our theory can be adjusted if somebody comes up with new experiments that don't support the theory. Then we may need to adjust our theories. And history is full of scientific theories that have been proposed and then changed over the years in order to try to understand the world better. Now, it's important to realize a theory does not become a law. The laws of science are not negotiable. If you observe things and you see how the world works, simple statements that describe how the world works, not explain how the world works, but just describe how the world works, are in fact observations. So if my observation was that students in first hour chemistry were tired, then I would simply say there is a law of students being tired in first hour chemistry. Now I might have various explanations for that. Maybe that they're not getting enough sleep at night, that they're all playing video games at night and they're not getting enough sleep, and so that's my theory, which I could then test by maybe observing them and seeing what they are doing, whether they are or are not getting sufficient sleep at night. Maybe it's just because they're all in band and before school they have some kind of activities that they do, and so these preschool practices or whatever are tiring them out. There's various explanations, and so we need to test and see what the proper explanations are. But the laws themselves are simply a description of what we see. For example, Antoine Lavoisier observed that anytime a chemical reaction occurs, the mass does not increase or decrease, that the chemical mass, the mass of the chemicals involved in the reaction, is constant. And so he described his law of conservation of mass, that in a chemical reaction, mass is neither created nor destroyed. Now, sometime after Antoine Lavoisier, it was proved that, or it was shown that that a chemical reaction is simply a reorganization of atoms, and that the atoms have the same mass before and after, and so that's why mass is neither created nor destroyed. So that's the atomic theory. The atomic theory is all matter is composed of small indestructible particles called atoms. John Dalton. The theory explains the law of conservation of mass and many other observations. So let's test your understanding. Which of these would most likely win you a Nobel Prize? A stunning new hypothesis, a theory, or a law. So what do they most likely give out Nobel Prizes for? People who discover a new law, propose a new theory, or simply have a stunning new hypothesis? Well, most likely, the answer here should be a theory, most likely, because a theory is the highest level of scientific understanding. It's our ability to not only see what happens in the world, but try to explain it as well. These explanations are the hardest ones to come up with, and so the most likely to deserve a Nobel Prize would be maybe a new groundbreaking theory. So what is chemistry? It's the study of matter. So without chemistry, we wouldn't be able to understand life. Life itself would not be possible. Life has a series of chemical reactions. Billions of chemical reactions are occurring right now that allow your body to work. There are various chemical reactions outside of your body that help your body, that help you, in fact, stay alive as well. Without the chemical reactions occurring in plants, there wouldn't be oxygen in the air for you to breathe. There wouldn't be food for us to eat. So we need these chemical reactions to stay alive. So as we understand those chemical reactions, then we can understand how to keep our patients alive, how to heal our patients by understanding the chemical reactions. So because these chemicals are part of our daily life, we are in fact all chemists. So we said that we're going to study chemistry and measurements. Let's switch gears to measurements. Chemistry is a quantitative field. We don't simply make observations about color or changes that may be occurring in the matter, like maybe it's changing to a gas or maybe it's giving out smoke. These are observations that are important in chemistry, but we also need to quantify things. We need to work with numbers. Things like the length, the volume, the mass, the temperature. These are important parts of understanding chemicals, is understanding numerically their properties. So we think about measurement. Measurement, for many of you, goes back to the English system of measurement. Many of you are most familiar with the English system of measurement. And in the English system of measurement, things like the length that you would measure things would be based on some arbitrary quantity, like the length of maybe the king's foot. So the foot, 12 inches, is actually the length of a man's foot. And so the king, maybe he's the standard. So the length of the king's foot. You get a king with shorter feet, you have to change the measurement of the foot. The foot no longer is the same amount of length. So I guess you would say when the king dies, you have to get a new ruler, right? New ruler, get it? Okay, with each new king, the measurement would have changed. So we have inches and 12 inches in a foot. We have ounces and pints and ounces and pounds. We have feet in a mile, yards in a furlong. Maybe if you know something about horse racing, you know that furlong is a fraction of a mile. Pounds, a large number of pounds in the English system is called a stone. So there's a variety of quarts and pecks, bushels. These are all volumes that are used in the English system. Now, many of us probably couldn't even come up with a lot of the conversion factors for these. Maybe you know how many inches in a feet. You might know how many feet in a mile, but ask someone how many yards in a furlong, they probably can't tell you now. So this system of measurement is not sufficient for doing good science. By the way, here are some of those numbers if you're interested. 12 inches make a foot, 16 ounces in a pound, 8 quarts make a peck, 2 pecks make a bushel. Pretty sure that's right. So often it would be based on the size of the king, so we say the measure of a man. In the sciences like chemistry, we want to use the metric system. These are more standard. You set a length and that stays the same. Doesn't matter who the king is, right? The meter is a standard length. The liter is a standard volume. The gram is a standard mass. Celsius is used to measure temperature. So we have standard units in the metric system. Unlike the English system, it's based on a variety of numbers like 16 and 32 and 5,280 and 12. The metric system uses everything in bases of 10, in other words, multiples of 10. Here's a little diagram that shows the metric prefixes and how to scale up and scale down from your unit. Notice the unit is sort of in the middle there as where the word units is. Kilo, which has a prefix K, means 1,000 of something, or 10 to the third of something. Hecto, 100 of something, 10 to the second. Deca, 10 to the first. The multiplier, if you say meters, is just 1. 1 meter equals 1 meter. Deci, 1/10. 1 decimeter equals 1/10 of a meter. 10 to the minus 1. Centi, 100th. Milli is 1,000th. Micro is a millionth. Some people remember these basic units with King Hector doesn't usually drink cold milk for kilo, hecto, deca, unit, deci, centi, milli. Just a little mnemonic there. The mitochondria would be moving the decimal to the right. 1, 2, 3, 4, 5, 6, 7, 8. 2.5 times 10 to the minus 8. So to write a number in scientific notation, we want to convert the number to a coefficient between 1 and 10. So that's important. You don't want 25 times 10 to the 12th. You want 2.5 times 10 to the 13th. Count how many places the decimal had to be moved. And then if you move the decimal to the left, then you know the exponent is positive. If you move the decimal to the right, you know the exponent is negative. So 25 trillion is 2.5 times 10 to the 13th. And the other one we said was, I believe, 2.5 times 10 to the minus 8. Let's try some for practice. This is how many tons the weight of the Earth is. Now starting on the right, at the end of the number, let's move the decimal. 3, 6, 9, 12, 15, 18. Looks like 21 spaces is where the 21 place values is how many places we have to move the decimal. Volume of the Atlantic Ocean, that's another big number. 3, 6, 9, 12, 13, 14 would put the decimal between the 3 and the 5. And that would give us the right number of places for our exponent. And then the mitochondria we talked about earlier, 0.00000025 meters. 5.972 times 10 to the 21st, 3.55 times 10 to the 14th, and 2.5 times 10 to the minus 8 meters. So notice the numbers have a certain number of digits in the front for the coefficient. It's got an exponent, which is where the decimal goes, and then it's got a unit. Units are important in science. Now besides measurements, there's another type of number we often use in science called a counted number. There's a distinct difference between counted numbers and measurements. On a measurement, you're going to have to use at least some degree of estimation. But if I asked you to count the number of dogs in this wagon, I think you could do that perfectly. There would be no need to estimate. It'd be a counted number. 1, 2, 3, 4, 5, 6, 7 puppies, right? And you know exactly how many there are with no degree of uncertainty at all. The number of puppies are 7. It's a counted value. And there's no decimal involved. There's no extra point something. You can't have 7.2 dogs. If I asked you how many eggs in a dozen, you'd take a carton with a dozen eggs, count them, you would get exactly 12. It's a counted number. It's an exact number. It's not something that you have used an instrument and gotten some kind of decimal value for. It's simply a counted number. In fact, 12 is the definition of a dozen. There's counted numbers, and then there's measured numbers. When you measure, you're going to be comparing the object to some standard, and it's not going to be a perfect relationship. You may say a rock weighs 3 pounds, but it doesn't weigh exactly 3 pounds. It's got a little more, a little less than 3 pounds. The pencil may be 6 inches long, but is it exactly 6 inches long? Is there some fraction of an inch that it is shorter than 6 or greater than 6 inches long? Measured numbers aren't exact, so you need some fractions. Maybe it's 6.5 inches for the pencil. Maybe it's 3.25 pounds for the rock. Or maybe if you're measuring with a meter stick, maybe it's 1.32 meters. There's some extra besides the whole number. There's some extra piece of something that you have there, and that's usually true when we have some kind of measured number. They don't come out perfectly to a whole number. So that's one of the troubles with measurements. If I asked you which measurement is most accurate for the distance to my friend's house in California, knowing that I live in Illinois and that California is about halfway across the country, and that from New York to LA is known to be about 3,000 miles, and that we're about halfway in between, I might say that it's 1,500 miles to my friend's house in California. Maybe I go on Google Maps and I Google map the distance between my house and or here and my friend's house in California, and it tells me it's 1,510 miles. Well, obviously 1,510 miles is a little more accurate than 1,500 miles. Maybe what I do then is when I drive the distance from here to my friend's house, I take note on the odometer on the dash of my car, and I calculate from the odometer that it's 1,512.5 miles. So that is even more exact. So that's one of the troubles with measurements. Measurements are going to be more accurate if they show more digits, or if you use an instrument that allows you to show more digits, it means that the measurement is more accurate. The number itself is telling us something. So it's not simply the size of the number and the unit of the number, but it's the number of digits shown becomes an important part of the measurement. So I think you know where we may be going with this. The number of digits that we're allowed to show gives some information about the accuracy of the measuring instrument and the degree of carefulness of the user of that instrument. So if we are going to measure, we have to take into account not simply what the number is, but how precise is our instrument. Now, measuring like a scientist means that we use all the marks given by the instrument, but we also add an extra mark by reading between the lines. In some places where the spaces are far apart, you can estimate up to 10 spaces between the lines. So if we look at letter A here, and we take 4 and 5 and we estimate between the lines, I would say maybe you should write down your own estimate here that this is probably halfway between 4 and 5. So that would mean we should write down not just the 4 or the 5, but one more digit. In other words, 4.5 centimeters might be the length of this piece of wood based on the measurement from this ruler. If we get a better ruler, letter B, we might find that with an extra set of lines on this more precise ruler, that we can even estimate an extra digit. For example, now that we have a more accurate ruler, we see that we are in fact between 4.5 and 4.6. So maybe we say 4.57 or something like that centimeters. Now this comes up quite frequently. Letter C. A lot of students will look at this and say 3 centimeters. And they will look at it as, well, it's right on the line. That's why I call it 3 centimeters. I cannot estimate between the lines because it's right on the line, 3 centimeters. Well, you could estimate between the lines, and so because you could estimate between the lines, you should call this 3.0 centimeters. The marks are 3 and 4. That means if you estimate between the lines, you get one more digit, 3 point something. This one happens to be right on the line, so let's call it 3.0 centimeters. You should let the people know that you have measured this to the nearest tenth of a centimeter. So in the first box, letter A, see here with this black lines, these are our own imagined lines. We are eyeballing it, we are reading between the lines, and we are inventing in our mind these extra spaces here that we can try to estimate, 4.5. Maybe 4.55. I think it's a little further to the right. Maybe 4.56 or 7. But it's an estimate, right? Letter C, 3.0. Don't say 3 centimeters. It's 3.0 centimeters because you have the 3 there, but what if you read between the lines? Now there are cases where the spaces may be so close that you could only estimate one maybe gap between those lines. For example, if 3.4 and 3.5 were very close together, you might not be able to see close enough to be able to tell 10 spaces, but you might be able to see if it's on the line 3.4, on the line 3.5, or in between. And so maybe you would say 3.40, 3.45, 3.50. That would be one instance of reading between the lines but not getting 10 segments, but simply 2 segments. If the lines are very, very close together and it's hard to tell 10 segments, maybe you could at least estimate 2 segments and see if it's 3.40, 3.45, or 3.50. The number of digits that we show in our measurement is called the number of significant figures. These digits are called significant figures. The simple definition of significant figures is all the measured digits. All the digits you can measure, and especially that last one you measure by reading between the lines, these are called our significant figures. So let's check you. What would you say letter A is? Maybe write down your answer. What do you think the answer for A is? What is the length of this stick based on the ruler? What about letter B? What do you think you should write down for letter B? Keeping in mind all of the digits shown plus one more digit that you estimate. So for A, maybe you came up with 4.3. Maybe you said 4.4. Maybe you said 4.2. Remember, the last digit can vary because different people see it a little differently. It is an estimate. The last significant figure is always a bit of an estimate. What do you think about letter B here? If you had the extra lines on letter A, maybe you could have said 4.35. But you're not supposed to give 2 extra digits if you don't show, if you only show the lines for the whole numbers, you should only show 1 more digit afterwards. Letter B, maybe 3.1, right? If you had the lines, maybe you could say 3.15. But if you don't have the lines between 3 and 4, you just have to say 3.1. Now here are some little tick marks between the lines, between 9 and 10. So let's think about what we would say the length of this green line is if we lined it up with a ruler labeled like this. Do you think it'd be 9.15, 9.20, or 9.25? Keeping in mind where the 9 is and how many tick marks there are between 9 and 10, and then how many tick marks the green line is to the right of 9, I think we would say 9.25. Okay, significant figures. All the digits in a number that you observe as data are automatically considered to be significant unless the number is a 0. Some zeros are not considered significant figures, some are. All digits in scientific notation are significant. That's, first of all, realizing that in scientific notation, all the zeros shown in a scientific notation number are considered significant figures. Zeros between non-zero digits are also considered significant figures. So 101, the zero trapped between the ones, would be a significant figure. The zero at the end of a number after the decimal is going to be a significant figure. So when there's a decimal in the number, zeros at the end are considered significant figures. For example, if somebody says 4.0, there would be no reason to say 0.0 unless they measured that zero. If they didn't measure it, if it's not a measured digit, then they wouldn't say 4.0. They'd simply say 4. Now, zeros at the end of a number before a decimal are not significant if they are at the end of the number. For example, 40, the zero comes before the decimal. 40, the zero is not a sig fig. You can't say 40 without having the zero there. And so it doesn't mean you measured the zero, it just means you need the zero in order to hold a place value. So just holding a place value doesn't make a zero a sig fig, significant figure. Now, zeros at the beginning of a number after a decimal are also not significant because they are placeholders. For example, 0.0007. Those zeros are at the beginning of a number, and so they are simply placeholders, so they are not significant. So zeros in the middle between non-zero digits are significant. Zeros in scientific notation are significant figures. But zeros at the end of large numbers, like 400,000, those zeros are not significant figures. And then zeros at the beginning of very small numbers, 0.0007, those zeros are not significant figures. They're just placeholder zeros. They're not measured zeros. So that could be a little confusing. There is a trick. A former Chem 106 teacher, Katie, came up with this. If the number has a decimal point, then start at the beginning and all of your leftmost non-zero digit numbers count, and numbers after it to the right are significant figures. When the decimal is present, zeros to the right are significant figures. 805.0. If the number doesn't have a decimal point, then starting at the end, rightmost, non-zero numbers, count those, and then all the numbers before to the left as significant. 8050, I would start counting here from the right. I would say on the right the 0 is not a sig fig, but the 5 is. So starting at the 5, count all the way to the left. 508, that's 3 significant figures. So 805.0 has 4 significant figures, but 8050 with no decimal present has only 3. Let's check you on this. 0.030 meters. Write down how many significant figures you think it has. Remember, the decimal is present, so start counting with the first non-zero digit, the 3. 0.03. The zeros on the left are not sig figs, the 3 is, and the 0 after it is. So that would be 2 sig figs. 4.05, here we have a trapped 0, 0 trapped between non-zero digits. Remember, those are significant figures, so that would be 3 for letter B. 0.0008, the decimal is present, so start counting from the left. Start with the first non-zero digit, which is an 8. There's no digit after it. It's only 1 sig fig, only 1 significant figure. And 150 grams. Here the decimal is not present, so we start with the first non-zero digit as counted from the right. The 0 is not a sig fig. The 5 and the 1 are significant figures. So A, 2 sig figs. B, 3 sig figs. C, 1 sig fig. And D, 2 sig figs. That is a skill that will show up on this first module quiz, is your ability to count significant figures in measurements, but also the ability to take a picture that shows a measurement being taken and estimate between the lines, as we did on the previous activity. Now, what do we do when we've measured numbers? We have a certain number of significant figures, and then we perform mathematical operations on them. For example, multiplying sig figs. When multiplying significant figures, the answer will have the same number as the fewest number in the problem. This is also the rule for division as well. 25.6 has only 3 sig figs. 13.442 has 5 sig figs. So when we multiply these two numbers and get 344.1152 on our calculator, we round it so we only have 3 sig figs. So 344, we look to the right. It's a 1, so we stay at 344. We don't round up unless the number after the last 4 would be a 5 or larger. The rules are different for addition and subtraction. When adding and subtracting with significant figures, the answer is going to have the same number as the fewest decimal places. 17.134 has 3 decimal places. 245.2 has only 1 decimal place. 3.1187 has 4 decimal places. So the 2 on 245.2 limits our significant figures in our answers to 1 decimal place. 265.4527 would round up to 265.5 when we record our final answer to this problem. The rounding is when you draw a cutoff line after the last significant figure, and then if the number is a 5 or greater, you round that digit up. If it's a 4, 3, 2, 1, or 0, you stay with the number. You don't change the number. Just drop the digits. Truncate the number. Okay. As you know from Chem 1, converting between units is important, so all hail the conversion factor. Many problems in chemistry can be solved through the use of conversion factors. Probably the most common mathematical operation we use in chemistry is the use of conversion factors. You probably use conversion factors every day but don't realize it. For example, how many inches are in 2 feet? Well, a foot is 12 inches. 12 inches would be a conversion factor. 2 feet times 12 inches over 1 foot, right? 12 inches over 1 foot would be the proper conversion factor. 2 feet times 12 inches over 1 foot equals 24 inches. The feet cancel, and you have your answer 24 inches. What would be conversion factor for yards and feet? 1 yard equals 3 feet, so quarts and gallons, 1 gallon equals 4 quarts. Meters and kilometers, 1 kilometer equals 1,000 meters. So we could write conversion factors based on those equalities. Let's try a problem. If a pound of apples costs $0.95, how much will 2.60 pounds cost? Well, our conversion factor is 1 pound equals $0.95. 2.60 pounds times $0.95 over 1 pound, $2.47. Pounds cancel. Unit is going to be dollars. Note here our conversion factors are always considered exact, so they do not figure into the sig figs. Now in the medical field, you won't be using gallons or kilometers or kilograms. You'll probably be using small numbers like grams and milligrams, even micrograms and cc's or cubic centimeters. These are typical small quantities of medicine that you use in the medical field. Let's try a problem with that. Neotigacin, used to treat some cases of psoriasis. The dosage is 25,000 micrograms, but the pharmacy only has 25 milligram tablets. So how many tablets should the patient take? That might be a problem you have to solve if you were a nurse. 25,000 micrograms. If you think of a gram being 1,000,000 micrograms, then that conversion factor, that first conversion factor there, would convert your micrograms to grams. Then you could go from grams to milligrams by multiplying by 1,000 milligrams over 1 gram. And then maybe you convert to tablets by saying 1 tablet equals 25 milligrams. If we do a lot of canceling, we find out that we end up with 1 tablet. 1 tablet, 25 milligrams, is in fact the same as 25,000 micrograms, but by the proper conversion factor technique, you can show that that's true. Another kind of problem you might be involved in would be a problem using density. Density is mass over volume. The units for density are going to have both a mass unit on the top and a volume unit on the bottom. For example, if an object has a mass of 25 grams and a volume of 10 milliliters, what's its density? Well, 25 grams is mass, 10 milliliters is the volume, so 25 over 10 is 2.5 grams per milliliter. Notice we have 2 sig figs instead of 3 because 25 has 2 sig figs and 10 has 3.